Hi all, I welcome you all to the next lecture today. Today we are going to start introduction about orbital mechanics. Here Professor Ravi Kumar, School of Mechanical Engineering, Shastra DMTV University, Tanjore. I welcome you all here with a new discussion today. In prior lecture, we have covered about different types of rockets, their working principle, as well as applications. Today, I will give you a detailed explanation about various types of you know laws available for studying the orbital mechanics, right? Types of planetary motions, right? As well as we'll see some of the applications, right, of those concepts. So let's start our journey of orbital mechanics. So till now, whatever we have discussed, right, we have given more emphasis, right, on the field of aeronautics. So aeronautic is the branch of engineering which basically deals with design and development of vehicles which are particularly suitable for flying in the Earth atmosphere. Or we can say that aeronautics is the branch of engineering which develop the vehicles, right, which requires air for its operation, right, and that's why they are totally dependent on the atmospheric properties. Or we call those vehicles as air breathing types of vehicles, right? So all the aircrafts, right, comes under the category of air breathing vehicles. Right. So aeronautical engineers basically are experts in designing the vehicles, right, which are basically being used in the Earth atmosphere. Clear? So in early up to 1965, more and more work being diverted towards the development of aircrafts. So space race basically started only in 1970s. So a lot of work was done immediately after that. Until today, basically, we are progressing and exploring the different corners of space. Still, a lot of things are basically mystery for us, and we need to discover those. So, the driving force behind the advancement of aviation has always been the desire to fly higher and faster. To fly so high and fast, we must go to the space that is beyond the limits of sensible atmosphere. In this case, the motion of vehicle takes place only under the influence of gravity and possibly some types of propulsive forces. However, the model of propulsion must be entirely independent of the air for its thrust. That's why the term came non-air breathing engines. So non-air breathing engines are suitable for the space exploration. Therefore, the physical fundamentals and engineering principles associated with those vehicles, right, which are suitable for space explorations will be entirely different than those which we are using in air breathing engines. Alright. So if we look at the vehicle categories, right, which are required for space exploration, our first category is called Earth satellites, right? So these satellites used to be launched with enough velocity to go into orbit about the orbit about the Earth. The velocity by which they need to be launched will be in the order of 7.9 kilometer per second, right? This much velocity is needed to send the vehicles right to the lower Earth orbit, and these satellites will be orbiting right in a elliptical manner around the Earth. So this is the historical picture, right, of Skylab, a satellite. Basically, the Skylab was the space station, the first station launched by the US. Launched by the US. So they launched it in way back in 1975. So the exact date is on February 8th, 1974. Right. They placed this space station right in the lower Earth orbit, right? And the total crew they went on this mission were four, right? They launched it, right? They placed it in lower Earth orbit and returned back on the Earth. Then this Skylab basically spent about more than 6 years, right, orbiting the Earth, and finally, right, it was actually destroyed, right, and some of the portions of it actually found in our Indian Ocean as well as in Australia. So we can say the total operation of this Skylab was started from 1975 and it was ended in 1971 itself, right? So on July 11th, right, about 35 years back, right, this was the NASA's basically non-operative space station that got crashed and finally fall on the Earth atmosphere. Some portion, some parts of this space station were found in the Indian Ocean, and some were recovered from the Australian Ocean. So, with this, actually, NASA gave an idea to have a international space station. So, what is basically an international space station? It is nothing but it is a station in the lower Earth orbit which which give the habitant an environment just like on Earth atmosphere to explore into the space. So NASA had the idea of space station 4 years before the Skylab was eventually launched. It was believed that it has to be developed much earlier. So as I mentioned that the USA's Warner von Braun, this is one of the scientists, right? He spent most of his time, right, in developing the equations about the space mechanics, and he has also given an idea to develop the international space station so that the astronauts which are going into this space can spend some more time in exploring the information about the space. And the final outcome of his efforts were the Skylab, and then Skylab 1 came, then Skylab 2 also came into the existing immediately after the Skylab 1. Second category of vehicle is lunar and interplanetary vehicles. These vehicles need to be launched with enough velocity to overcome the gravitational attraction of Earth and travel into deep space. So the velocity requirement for launching these lunar and intraplanetary vehicles are around 11.2 km per second or larger. Right. Such trajectory the trajectory by which they will be going into the deep space will be of either parabolic or hyperbolic. So you can look at this pictorial presentation. It will be launching like this, will be going on circular orbit, then finally it will be hyperbolic, right? And keep on going, and finally it will land over the moon. So this is the trajectory, right, of a space vehicle from Earth to the moon. And basically, these are of two types, maybe parabolic or maybe sometime hyperbolic. Third category of vehicle is space shuttles. Already I given you some idea about it in previous lectures. So space shuttles are designed to take off from the Earth's surface, perform a mission in space, and then return back and land on the Earth's surface. So it is a all self-contained vehicle, right? So it has to be designed in such a way that it should have capability of re-entry, right? As well, it should have sufficient LYD ratio that allow the pilot to land the craft just like an airplane on the earth. So this pictorial presentation is giving you the procedure of launching and re-entry into the earth atmosphere. So let's suppose this is my orbit, circular orbit, right? And my space shuttle is launching from this point of earth. This launch station goes like this and finally comes into the orbit. So this is the orbit, and if it is wanting to return back, this is the re-entry pattern. So it will not be similar like here almost you are getting a parabolic curve, but here it will not be parabolic. It will become hyperbolic now, right? So because here we are having more power, right, when we are launching it, but when it's coming, may not have that much sufficient power. So it is entering here, right, and then finally it comes in this way and land over here. So this is one of the notable person who spent his life in developing an island, right, of observatory. From there he clearly gave the positions of Mercury, Venus, Mars, Jupiter and Saturn, as well as Moon. So the name is Danish astronomer Tycho Brahe, right? He had developed the island observatory, and from there he made an accurate measurement of relative positions of these planets, especially Mercury, Venus, Mars, Jupiter, Saturn, as well as Moon. Second significant name in the space mechanics development, right, or the laws development for understanding the space, understanding about the space or about the planetary motions, right, is given by the Johannes Kepler, and he gave the Kepler's law. You might have some idea about it from your basic physics, subject. So, Austrian mathematician Johannes Kepler, he was interested in how the planets move around the sun. He went to the Tycho's island, as earlier I mentioned, the Tycho island, to get these accurate measurements, and finally started thinking about how actually these planets are moving, and he come up with some rules which clearly give an idea how planets are moving about the solar system, and what happens where basically our solar system is existing. Exact point was given by the Johannes Kepler. So who is Kepler basically? If we look at his own background, Johannes Kepler came from a poor Protestant family in Germany. He became aware of Copernicus' work at the University of Tübingen, where he completed a master's degree. He then began study theology, but before finishing his degree, he was offered a job of teaching mathematics at Lutheran school in Austria. Kepler was impressed with the Pythagorean idea that the numbers underline the mysteries of the cosmos. He was especially interested in why there are only five planets and why they orbit at the distances they do from the sun. So, this basically intensifies his curiosity about understanding planetary motions, right? And particularly, he was not convinced why only there are only five planets, there may be more. So that's the turning point where he utilized the knowledge of mathematics, right, and Pythagorean ideas to develop a relationship to understand the relative motions of these planets. So Kepler's made us some pioneering conclusions about the geometry of planetary motion. Kepler induced and published the three laws of planetary motions, obtained strictly from exhaustive examinations of the astronomical data. But at the time of Kepler, right, he was not aware about the Newton's law of universal gravitation, because the Newton's law basically came after around 3 to 4 quarters of the century later. So Kepler actually was not having advantages of Newton's law of universal gravitation or Newton's mechanics. But Kepler gave important, outcome, and even today we are using those laws to understand the planetary motions. So Kepler's three laws are as important today for the understanding of artificial satellite motions as they were in 17th century for understanding the planetary motion. So Kepler's first law, if we look at the Kepler's first law, he gave the Kepler first law. First of all, he said that all the planets are moving in elliptical orbit. So this is an elliptical orbit, right? If you look at the pictorial presentation, the rightmost point is called perihelion and left side is called aphelion. So they are two focus of ellipse that you already know. He identified that sun lies on one of the focus near the perihelion, but on the second focus there is nothing. So nothing lies at the second focus, right? So sun lies exactly at the first focus point, and all the planets are basically orbiting about the sun, right, about that particular focus point. So first law says that planets move in elliptical orbits with the sun at one focus of the ellipse, right. This is the first law given by the Keplers. Immediately after that he came up with the second law. Then he said that a line from the sun to the planet sweeps out the same or equal area in equal times. That is, planets don't move at constant speeds, right? They may not be traveling at the same speed everywhere. So look at this example. This is the position of perihelion. This is the position of aphelion, right? Let's suppose I am considering planet. Initially it is here, right? I connected a line from sun to planet, and I have fixed the timing of 30 days. In 30 days it is going from here to here, right? And the area swept by this line is given by this John. Similarly, let's suppose I'm considering a planet now near the aphelion point here, and I connected with the sun. In 30 days it travels from here to here, all right, from here to here, same time duration I have fixed on both sides. And finally, when we observed it, the area sweeps by the line connecting planet and sun in equal time is exactly equal. So if we look at this area is slightly wider. But if you look at this area, it is having larger length, but area is very narrow. When we find out the magnitude of this area and this area, that is exactly equal. So the area swept out in 30 days periods are equal. This is this was the significant discovery, one of the Kepler's, right, contribution towards understanding the planetary motion. And after the second law of Kepler's, he devoted almost 10 years, and after 10 years of rigorous, you know efforts, he came up with the final law, third law. So Kepler was committed, right? He is charged for 10 more years to find out the mathematical law to describe the motion of planets around the sun in harmony of the world. In 1619 he enunciated his third law. As per third law, he said that the time duration, a period of the planets from one point to another point exactly predicted. So he said period of the orbit square is directly proportional to the semi major axis of the orbit q. So in mathematical form, period square is directly proportional to aq. A is known as semi major axis, right? Q. If these two quantities are proportional, we can insert a constant here, right? Proportionality constant. So P square is equal to K AQ, and this K basically depends on the units of P and A. So if we remove this proportionality constant, we can write P square is equal to K AQ, where P is the period of orbit, right? A is basically semi-major axis orbit, right? It talks about that. So this was the important discovery. This is the final law given by the Keplers. So using the Kepler's third law, we can say P square is equal to K Q, where K is some constant number. So we can find K by expressing P as Earth orbit in years, right? And A is expressed in terms of distance from Sun and Earth, right? So if we put these values, we can express this distance as 1 astronomical unit, or you can say 1 AU. This is basically for A. This distance from Sun or Earth is nothing called 1 astronomical unit. So if we substitute 1 and 1 both sides, we can say it is K is equal to 1, right? So basically P will always be in year because P is talking about the period and A talks about the distance from Sun or Earth, and this will always be in astronomical unit. So the unit of A will be in astronomical unit and P will say the period, right? So period will be in years. So with the help of third law, we can exactly predict how many more years your planet will take from one point to the another point. So let's suppose this is one of the simple numerical problems of based on the third law. An asteroid is found and its orbital semi-major axis around the sun is measured to be 4 astronomical unit. So this is basically small a is given. What is the period of its orbit around the sun? So you need to calculate the period. So you can use the formula P square is equal to AQ and you can find out the period simply. So P square is equal to AQ, P is in year. So just put the 4 astronomical units, just 4Q, you can get the period. Period is coming around 8 years. That means it will orbit around the sun in 8 years. Like that you can calculate the period. Next one is celestial dynamics. But what makes the planets move in this way? That was still a big question in front of the Kepler. So Kepler has now lost Aristotle's theories of motion and there was nothing to replace it. So he realized that planets move more slowly the further they are away from the sun. So this is not exact reason why planets are moving in this way. He made this analogy that a planet is going too far away from the sun, it appears to be moving slowly. Does this mean it is the sun that is the source of their motion? Right? Second question comes, is it the sun which is basically making your planet to move? Then Kepler guessed that the planets are moved in some ways by the sun, and the further away a planet is, slower its orbits. So he thought it might be some kind of magnetic force. He said maybe a magnetic force which is acting between the planet and sun, which is making the planet to move. But that is not a real, reason why planets are moving in that way. So Kepler's intellectual legacy, if we look at, Kepler gave 3 laws of planetary motion, and these are basically of an intellectual higher watermark. The sun was now firmly at the center of solar system. He clearly predicted that mathematically that sun is at the center of solar system. For the first time, Kepler introduced celestial motion that was not circular. Prior to him, people were thinking that motion is circular, but he clearly proved by mathematics that motion is not circular, it is elliptical. The Greek idea that motion in the heavens must be circular had lasted over 2000 years. And after that, immediately Kepler gave clear explanation about the motion. He said that it's elliptical. So Kepler was aware of the fact that his model was lacking in dynamics. So he had discarded Aristotle's model and bathed his theory of motion, but there was now no theory to say what made the planets move in these ellipses, right? So when he discarded the Aristotle's model, right, then there was no theory left with which can exactly say why planets are moving only in ellipse. But Kepler suggested there was some magnetic force emanating from the sun which is responsible for making your planets to move in the ellipses. So this became a major intellectual problem in the 17th century, and only in 19th century, after the discovery made by the Newtons, we came to know there is a gravitational force which is basically making your planet to move in those ellipses, not the magnetic force. So this is what I wanted to share with you, right? So today basically I gave you some idea about what are the different kind of orbital motions, right? And we have discussed in detail the Kepler's contribution, right, in understanding the planetary motions, and he has clearly gave us an important idea that sun is the exactly at center of the solar system, and around this all planets are moving in ellipses. So at his time, as he was not aware about the gravitational laws, so he could not be able to correlate the emotions in terms of gravity. But on other way, he said that there may be magnetic force emanating from sun which is basically making your planets to move in those kind of ellipses. So prior to Kepler, it was believed that all the orbits are circular. So all the motions made by the planets are circular. And Aristotle also, right? He basically observed from the Earth, and he basically guessed that planets are moving only in circular path, but that was not true. It was later proved mathematically by the Kepler that it is not circular, it is an elliptical orbit, and it is having two foci point. At one foci point, our sun is situated. On second foci point, there is nothing. And finally, he has taken the semi major axis as one of the criteria, and also the distance of planet from sun is another criteria, right? That is also very important criteria. And using those two criteria, he clearly predicted the relative motion of planets around the sun. So first law that he gave was the discovery that all the motions made by the planets are elliptical. And the second law, immediately after the first, what he said that if we connect the position of planet with the sun, if we draw a line, that line will sweep equal areas in the equal time. Either you are on aphelion point or aphelion point, right? And perihelion point. So at 2 opposite points of ellipse, the line connecting the planet and sun will sweep equal areas. And he clearly said that as a outcome of the second law, that planets are not moving with the same velocity or constant velocity. Third law, for that he spent almost 10 years, right? And after that, he came up with very important discovery that period of rotation from one point to the another point and a planet is square is directly proportional to the distance from the sun q. So he gave p square is equal to eq, that is the third law, and there was a proportionally constant, and he finally proved that proportionally constant is exactly equal to 1, and the distance between from sun or earth is basically expressed in terms of astronomical unit, and period is in year. So if we know the distances, right, and we can find out easily the period of one orbit, right, and how many years it is going to orbit completely one rotation, that can easily be found out with the help of the distances. That is the third law, is the biggest contribution. So even though these were invented in early 17th century, but still today we are using the Kepler's law for understanding the Earth satellites, right? How actually they are moving, as well as the planetary motion. So with this, I'm closing the today's discussion. If you are having any doubt in the current topic, feel free to write in the comment section, or you can directly approach to me via my WhatsApp number. Right? Thank you for your patience for listening to today's lecture. See you all in the next class. Have a nice day. Good day.